Okay. Hey, everybody. So, today we get to talk about mixtures of Gaussians. Yes, I screwed up and did not get a pre-lecture out. My bad. I'm sorry. So it modifies a little bit of things. One, you didn't get a chance to see the math on mixture of Gaussians in a rewindable format. So, well, hopefully it works out just as fine with a live lecture on math. The second thing, of course, with that is that I keep encouraging people to watch the pre-lectures, and then I screw up by not putting one out. So I'm sorry. Life got in the way. If anybody would like to know, I did manage to rescue my comic books from the flooded garage, so that wasn't so bad. But here we go. Let's do the fun stuff. What is the idea of a mixture model? We've already seen k-means. Why do we need something else, right? Because fundamentally, an idea of a mixture model is kind of like a soft version of k-means. In k-means, a data point belonged to a cluster or it didn't. What we're going to do now is we're going to allow some uncertainty, right? Some probability that this data point belongs to cluster 1 and some other probability that belongs to cluster 2. And of course, these are probabilities. So all the possible clusters that a data point can belong to add up to 1. Okay? So I hope that immediately that sets you in mind this idea of a soft weighting or a membership, or as the literature likes to call it, a responsibility, right? What's the responsibility of cluster 1 for this data point? What's the responsibility of cluster 2 for this data point? That's soft. It's not just binary. It's not just 0 and 1. But that soft weighting parameter gives us a lot more ability to fine-tune our models. Okay. So, but other than that, it's kind of k-meansy. We have to assume that our data is generated by an independent processes, by a set of independent processes. We're going to call these clusters. And we're trying to infer what's the best mapping of data to clusters, and what's the best parameters of these processes to describe the clusters, right? So to show you this idea that things are more complicated than the k-means case, we also have this really cool feature where we can allow not just spherical covariance, but any shape of covariance we want. So these are the two things that are different than k-means. One, membership to a cluster can be a number between 0 and 1, not just a hard binary. Number two, the shape of the cluster's covariance can be restrictive or completely free-form. Right? So to show you these two things, just to make sure that it's all clear here, right? In this idea, we've got 3 different data generating processes: the blue, the green, and the red. And this is what the truth is of what created this situation. When we fit a Gaussian mixture model, then what we fit are, if we're assuming we're fitting 3 clusters, we fit the means and covariances. So this little cross shape, that's the mean, and this phantom shadow represents the covariance. Is this a spherical covariance? No, right? This is a full covariance. It enables any shape. It's not axis aligned, right? It's not like this or like this. And it's not a spherical like that. Note that each one of these 3 means can have a different covariance matrix. Okay? So each mean gets its own covariance if we do the full solution. So then the other thing that you can see here is if you look at the coloration of the dots from the model, this fading from one color into another is supposed to indicate the probability that we belong to a certain cluster. So the bright red data points in here, they all very certainly belong to this red cluster. But in this zone, the colors are a mix of red and green, because we're not certain which ones of the clusters these data points belong to, okay? Can anybody think of a mathematical tool that we already know for assigning something like how much does this one data point belong to red or green? Yeah?
The Z or T value, so the standard deviations.
The standard deviations, like, yeah, like the probability distribution function itself. The likelihood function. In fact, the likelihood that a single piece of data is generated by a cluster with a particular mean and covariance, right? Just follow that falling bell shape, and if your data point lies close in the upper reaches of the bell, it's pretty likely it came from that one. And if it's way out here in the tails, probably not, right? So like all this is super intuitive once you place the stuff you already know in a particular viewpoint mathematically, right? So let's get into it. How do we fit these things? Well, you already saw my little diagram with blue and orange. It's really the same thing. It's the two-step. The two-step is, we just use different words now because we're fitting in a different way, right? Step one is initialize everything and then go calculate what's called the expectation step. The expectation step is all about estimate the responsibilities for describing this data point given the parameters of the problem. And those parameters include two things. They include the distributions, right? Their means and their covariances, and also an assignment of which one of these things a given data point belongs to. Then once we've estimated that, we can do an update looking at maximizing the likelihood given those assignments. Given the way we've carved up the data within the first step, we're going to update the means and the covariances given what we've seen. And we're going to slowly iterate back and forth until we reach some kind of convergence criteria. So this is, in a mixture model setting, this kind of math is meant to do maximum likelihood estimation, right? What's the most likely mean? What's the most likely covariance? In a future lecture, we'll see how we can make a tiny little change and instead do the Bayesian thing and estimate distributions of means and distributions of covariances, okay? So all this, the original idea of EM, as it's called, expectation maximization, traces back to a cool paper from 1977. Maybe it's worth your time if you're feeling it, but you'll certainly see people cite Dempster, Laird, and Rubin repeatedly. So again, what's different here? Two things are different. During the E step, instead of just saying, am I closer to cluster 1 or am I closer to cluster 2? If I'm closer to cluster 1, yes, I belong there, right? It's binary, 0 or 1. Now we have this responsibility thing, which is really just the PDF, right? It's the probability, a soft value. Okay. We're going to add one more mathematical trick that is super common in this world, that is super confusing to newbies. It's the idea of taking something that you're like, oh, all I need is like probability of the data given the parameters, right? We're going to make life harder. We're going to insert a brand new variable into the mix. Instead of the probability of the data given the parameters, we're going to do the probability of the data given some latent variable we can't observe, but we know is affecting the situation. Okay? So it looks like this. This is a graph theoretic representation. Z is this latent variable, something we cannot directly observe, but we can infer. For instance, what we're going to do today is, this is the cluster responsibility. Right? Z is, what's the likelihood that a given cluster is generating this data point? Is it cluster 1 or cluster 2? Okay? So we know that this is, by the way, in this kind of a graph notation that we're seeing here, this says X is in some way caused by Z. The data we observe, to go back a couple of slides, the data we observe here is a function of the clusters, right? So this cluster responsibility, it affects the measured data. So we're going to break up what had just been a straightforward probability of the data into this two-step where we're looking at the joint probability of the data and the cluster membership. And it's equal to the prior probability of the cluster membership times the probability of the data given the clustering, right? Given the membership functions. I keep using membership function and responsibility interchangeably. I'm sorry about that. I'll try to settle down. So here's also a little clue. By setting this up, what we're getting to is that this mathematical trick is going to enable us to pull out that marginal on the denominator in a way that's really useful for EM. Okay? That's why we're doing this. This trick also enables us to integrate over all potential Z's so we can check all the possible membership assignments to a cluster, right? That's useful. The other thing it gets us is we can use this same framework later on to infer other unobserved things. Like if we get a data point that's got some missing values in the vector, we can infer the most likely missing values using the same trick. So this generic approach of break something obvious up into some latent thing that we can't observe and integrate over it gets us a bunch of cool stuff. Any questions on the concept, at least? It's time to get down and dirty with some math. Okay, so again, as you might have guessed, since I didn't do the pre-lecture, I'm having some real time crunch issues, which means also I've just chosen to blatantly copy-paste Bishop into some slides. My apologies, but let's actually understand what the math is saying. So here is the thing we're trying to get to. Whatever we're observing with the data, we have a probability of observing this data. And it is literally a mixture of Gaussians. Here is a Gaussian, right? A normal distribution. We get a PDF, the likelihood of X given the mean and the covariance, right? Everybody on board with this is just a normal PDF? Okay. So a mixture of Gaussians, like if they all contributed equally, that would just be sum over all the Gaussians, right? Each Gaussian, each cluster is assumed to be completely independent of the others, right? So that we just plop down data points from this guy, and we can add in data points from this guy, right? So we can just add them together. But we have this weighting function, this pi, okay? And back in k-means day, pi was just 0 or 1, right? A data point belongs to this cluster, or it doesn't. 0 if it doesn't, 1 if it does. Now we're going to let that be non-zero, okay? So, just to make your life super confusing, this is the formulation that's in Bishop, but you could just as easily have said, because we keep talking about this as z's, right? Okay, so in fact, that's the format we see here. We are assuming, in the end of the day, that this data point is generated by one cluster or the other, not both. Our responsibilities we're trying to estimate could be non-binary, right? But we're looking for the probability that I belong to this cluster. I'm looking for the probability that z of k is 1, that membership is 1, okay? So I'm looking for a hard assignment. What's the probability of a hard assignment? But I'm allowing pi to be a non-hard number, a soft number between 0 and 1. So that's why we are, in fact, not using z here, right? But I'm using pi to allow the soft membership. But what I'm looking for is the probability of the actual assignment being 1 or 0. Maybe? There's a lot more hands-on heads thinking right here than in the last couple of slides. So pi is a non-hard number, but z, we're looking for the probability that the assignment itself is hard. Okay. So we're going to rely on the fact that these things are probabilities. So pi has got to lie between 0 and 1. If we sum up all the possible pi's over all the possible clusters, they've got to equal to 1. And the assignment, the z, it's a one-hot vector. Zeros to all the clusters I don't belong to, 1 for the single cluster that I actually belong to. So if you put those two things together, you can say that the probability of z has just got to be equal to the product of all the individual pi's taken to the power of z. So anything that I don't belong to is going to be to the 0th power, right? So sucky. Okay. So all that says, when we come down to it, that we can get rid of a lot of those bullshit on the last slide. And we can just say that the probability of the data, given that I belong to the cluster, is simply the PDF of the cluster, unsurprisingly, right? All this math is just in service of breaking it down to the intuition we already had, of proving it mathematically. So in that case, then the probability of the data given our z vector, our assigning to clusters vector, is merely going to be the product of all the normals to the zth power. Right? And this enables us to go to the form where we can take our prior and our likelihood function and combine them together into a sum of pi's multiplied by their normal distribution. Thoughts, worries, concerns? Okay. So again, that relationship between pi and z. So Bishop offers you a view, two different views of the whole z thing. One is that you can see pi as the prior probability of the assignment, right? And this quantity that we can pull out, this so-called gamma of z, which is really just the probability that I belong to this cluster given the data, right? Probability that this data point belongs to cluster 1, this cluster case, given the data, is just the inverse, the Bayesian inverse of the thing we've already observed, which is a probability of the data given the clustering, right? We use Bayes' rule to just flip things around in the direction of the givens, right? So this view of the, the probability of I belong to this cluster this is the responsibility. This is this quote-unquote thing they call responsibility, right? It's how much component K takes for explaining the data. It's the ratio of pi times the normal for cluster K divided by the summation of pi times the normal for all the clusters, right? It's just how far out in the tails am I for cluster K? What percentage of that is it over, take that quantity over all the clusters? So it's the ratio of how close I am to this cluster in distance compared to how close I am to all the clusters. So that's the responsibility of component K. But you can also think of the same thing as a two-step, right? From prior probability, which is pi, into a posterior probability once we've made an observation. Two views, same thing. Okay. So here's where it gets down and dirty. Now that we've got all these definitions, we can find something to optimize. All machine learning, including fitting a mixture model, is merely defining some function and finding its minimum or maximum, right? So here's what we want to optimize. We want to optimize this thing we've been talking about, the summation of the weighting function, pi, and those normals, each one of those normals defining the different processes. To make it so that we can actually solve this as an optimization problem, we use our log trick, right? We just reviewed this previously during MLE. Take a function, take its log. The log of anything has got to be quadratic in the parameter space. If it's quadratic, we've got an optimum that we can solve for by taking the derivative and setting it equal to 0. Same as always. This is really just maximum likelihood estimation, but on some very particular things. So just like maximum likelihood estimation, we're going to take the log of the probabilities and then set them equal to 0. Set the derivative of the log of the probabilities equal to 0. And when we do that, we can, we got to take the log of some exponentials, and it comes down into this form. And we will recognize this thing right here as that gamma, or that responsibility term, right? This whole stupid ratio is the responsibility term. And so it's just do a little bit of rearrangement, right? Multiply this thing through, multiply by the inverse of the covariance matrix. Hey, who's my linear algebra wizard in here? Can you invert any matrix ever? No. There are absolutely matrices you cannot invert. So you cannot divide through by the covariance the way you need to do. So there are absolutely problem sets, data sets, where this goes to hell in a handbasket, okay? So the usual thing, if matrices are not full rank, stuff gets crazy. You can't get the inverse, okay? So there do exist problems you can't solve this way. Okay, but assuming that you can do it, then you just divide through, essentially multiply by the inverse of the covariance matrix. And guess what you find? The same thing you always find with maximum likelihood estimation. It's just the stupid empirical mean. But in this case, an empirical mean weighted by something. It's a weighted empirical mean. What's it weighted by? Once again, if we have some sort of means and covariance matrix, and I've got a data point, what it's weighted by is fundamentally how many standard deviations am I away from that versus how many standard deviations am I away from that. That's what it's weighted by. Does that make sense? At least intuitively, if you're not following the math in detail. Okay, so we've defined this kind of n sub k because that's just summing up all the responsibilities for all the clusters. We're going to use that in a minute. Okay, you can do the same thing to solve for the covariance matrix. Take that log likelihood function we already defined. This time, instead of doing the partial with respect to x, do the partial with respect to sigma. Now we're finding the sigma which optimizes, right? And the magic can happen. And what happened here? I don't know what happened to my magic. This should just say that, oh yeah, sorry, this is just, my bad. That is, in fact, the empirical covariance matrix, right? X minus the mean squared, right? This is the squared version of that in linear algebra land. Once again, weighted by our responsibilities thing. And you can do it a third time. This time, instead of doing the partial with respect to mu or sigma, we do the partial with respect to pi. Now we can update pi, which is how likely are we to belong to these different clusters. And it turns out that pi, I'm not going to go through this one, but pi is just how much responsibility do I have to this particular k cluster, cluster k, over the total responsibilities. It's really exactly what you expect. Again, all this math is just in service of showing you rigorously what you already kind of felt in your heart. Okay, so here is Gaussian mixture EM. Step one, the expectation step. We have to figure out how responsible each cluster centroid is for generating a particular set of data points. Once we have that empirical responsibility function, now what we can do is we can use that responsibility function here and here and even down here, right, to re-estimate all of our parameters. Yeah?
Why doesn't the NK cancel with the thing right next to it, like the nu? Isn't it the same thing, just on the polymer fraction?
Sorry, which way, where? 927?
In 924.
924.
The 1 over NK, why doesn't that cancel with the thing right next to it? The NK is written the same way.
That is a good question, I think, without being clear right now, that it's got to be a linear algebra thing.
Okay.
I guess X is columnar, and I'm not sure. I'm sorry. It's a good question, though. We should sit down and work that out. Maybe a conversation on Campus Wire. Okay. So, and we keep going back and forth between the E step and the M step, right? Rather than hard assigning data points to which cluster they belong to, and then moving the cluster means, we're soft assigning with that responsibility gamma and shifting the means of all the clusters according to all the data, right? Even data points, to go way back to the beginning of my slides. Oh, it's going to be slow on me, right? So even though this data point over here emphatically does not belong to the red cluster, it has some tiny, tiny influence when we update the means of the red cluster, okay? Because everything is finite between 0 and 1. Okay. The last thing I want to remind you of is the nature of covariance, right? The diagonal of the covariance matrix is, variable 1 or variable 2. It's the standard deviation along those axes. The things that are off the diagonal are combinations of multiple axes. This rho is Spearman's rho. It's Spearman's correlation between x and y in this case. Obviously, you can generalize this beyond a two-dimensional case in your mind. But in every position, it's whatever two rows and columns, whichever those two variables are. It's the interaction between those variances. Okay, so we saw this picture before. We have the axis-aligned stuff, right? And the spherical stuff. The spherical stuff is where all the things on the diagonal have exactly the same number in them, right? I've got the same variability along x as I do in y. And so the resulting variability is spherical. A little bit less constrained is the axis-aligned stuff, where there's no covariance, but we allow x and y to have separate variability, right? I have more variability in y than I do in x, but I don't have any covariability. I don't have anything going along like this. So those are specific formats for the covariance matrix, and we can constrain the models we build accordingly. If we think x and y are not correlated with each other, we would use spherical model building. So, independent rolls of the dice, if that's our model, we would keep x and y spherical with no covariance between them. That's a super simple model. We don't care about anything except one value. We don't even need a covariance matrix. We just need a single variance. In the axis-aligned case, the one in the middle, that says x and y are still independent of each other, but one of them's more variable than the other. So maybe something like if two variables are height and weight in a data set. Actually, that's a bad example. Those are correlated. Shit. Somebody come up with a good example. Independent variables that have different variabilities. Height and IQ, right? Not correlated as far as I know. Sorry, tall people. Okay. Or maybe it is height and weight. Height and weight are correlated. That means there's got to be covariance, and we're going to be in a situation like this one, maybe. Right? That's a full covariance matrix where there is, stuff off the diagonals that's non-zero. So again, the simplest versions, the axis aligned and the spherical, you're going to see the identity matrix in there. The identity matrix says, hey, diagonals only, people. We don't care about stuff off the diagonal. Okay, so all the math preamble is out of the way. We've got enough time to actually do this notebook. Yes. So if you look in the repo, there's a GMM notebook. I would like you to please pull and start up your Jupyter notebook and open that up. Okay? Because I want you to do this exercise. I promised some interactivity, and I mean it, goddammit. Okay. So it's notebook L07, Gaussian mixture models. If you need to, of course, it will work on DataHub. Hopefully you've got a working copy on your local computer if you hate DataHub like I do. Okay. I'm just going to execute the first bit of the notebook. All right, there's just a bunch of functions in the beginning. And then the next set is, let's get some data that's going to give fits to k-means. Okay? There we go. So my first question to you while you're working is, why will these particular data sets have a problem for k-means? We talked about this last time. What kinds of things are going to happen, say, on the top right that k-means is not going to deal with? Yeah?
It's not spherical.
It's not spherical. K-means assumes that all of the means have the same variance, and that variance is the same in all directions. Right? So this is got covariance in it, right? Like it's the off diagonals are non-zero in that top right. What about the bottom left? Why is that going to be problematic? Yeah? Yeah, unequal variances. K-means assumes the same variance for all of the means. So even though that one's spherical, what about bottom right? Yeah?
Different numbers of data points
And how does that cause k-means to collapse?
Because the silhouette score is going to be pretty poor because they're going to be drastically different.
You got it. Yeah, the silhouette score is the diagnostic, right? And what happens is that, again, the assumption of trying to fit equal variance structures here means that like a situation like that lower left cluster that only has like 6 or 8 data points and the others have 30 or 50, right? It just isn't true. The equal variance thing is not true, and the silhouette score will reflect that. Okay. So hopefully you've got this up and running, because what I want you to do next is we can show with the k-means how those break down, right? So these colorings show you the clustering now that was done with k-means, not the generating process, but the clustering. And you can see that in some situations, k-means does not deal well, right? The assumed equal variance has this yellow one taking a chunk out of the green. Actually, these unevenly sized ones here, it worked. It worked because they were so far apart. In a different one, it wouldn't have worked well, okay? So here's your task. Time to do some programming. I've got you set up to use a Gaussian mixture model. I want you to look at the scikit docs here and go see what the parameters of Gaussian mixture model are, try to understand them, particularly the argument for covariance type, okay? Once you've understood how those arguments work, I want you to change the covariance type of the models we're going to fit and explore all the covariance types and try to understand them. I'm going to come back to you in like 3-4 minutes, and we're going to talk about this. Yeah?
Why does k-means screw up in the top left?
Good question. So the top left, we are fitting, which you may not have quite noticed, is that we're only fitting 2 clusters. So the non-optimal number of clusters, it's a 3-cluster problem, and we said k equal to 2. In general, that's going to be difficult for everything, right? But what you're going to see is they're going to fail differently. So in a full model, right? We're looking at a full covariance matrix. Some interesting things happen. when we get to that non-optimal number of clusters, you can see that it is trying its hardest to imagine that as a single Gaussian, right? Because that's the model structure. You can see the covariance matrix in that shadow, where the darker regions are towards the center, towards the mean, and number of standard deviations away is reflected in a fall off of the gray, right? So k-means doesn't have anything like that, right? But we can kind of see what k-means would look like on that one. Oh wait, is it tied? Oh, I can't remember which one. No, it's spherical, right? And you got to imagine this is kind of what k-means is doing in the top left, except that the two would have to have the same size of shadow here, right? We don't have an option for spherical and tied. We only have one or the other. What do you think about tied? What does that do? What is the effect of the tied argument? Yeah?
It makes all of the covariance matrices equal.
Yeah, every single cluster has to have the same covariance matrix. So let me compare and contrast this to two supervised machine learning algorithms you may or may not be familiar with. Naive Bayes is a categorization tool, okay? It assumes spherical covariances. Linear discriminant analysis, or LDA, assumes tied covariances. It enables non-sphericity, but every single category has got to be described by the same covariance matrix, okay? And so these same, if you're familiar, if you happen to have used something like that in a previous class, this might make an intuitive kind of sense to you. And you can see in situations like this where like, you know, there's, like what if we don't have one here, but what if we had a real spherical and a real non-spherical thing, right? The tied result would end up producing this weird mishmash where the non-spherical cluster would be like too spherical, and the spherical cluster would have this cigar-shaped thing, and it wouldn't really fit neither of them, but it's an average between them. That's something we don't have on the data set, but it's kind of cool. So I ask you, I'd like a little bit of discussion, right? It's clear that full is the most powerful. It can fit the most situations well. But are there any situations where full would give us a bad result? Is it the case that the full argument is just what we should always use, and why do we have any of the others? Yeah.
I know when I did the full, on the bottom right, the green cluster, the covariance was like complete opposite versus where on the top right, it's pretty much fit.
Oh, on the full, sorry, what happened?
On the bottom right.
Okay.
When you change to full, the green cluster in the bottom right will be really weird or something, I'm pretty sure. Or it's like one of the other ones.
This,
Yeah, it was like, I think the green one is supposed to be like really stretched out.
Okay, so like in your opinion, the green one might be more cigar-shaped? Yeah. Okay, so I want to couch this idea in terms of the bias variance trade-off for those of you that have been in 118A. How would you imagine a more powerful model, how it could go wrong in terms of bias variance? Yeah?
Well, if you have something that's very simple, like it's all sphericals, but the sphericals are very close to each other, then there's a chance that it will like decide that the two sphericals are just one giant, whatever it's called.
Yeah, so fundamentally, if we have situations where we maybe don't have enough data, especially, to see the difference between two sphericals next to each other, right? That could look like a single cigar shape, right? So if we don't have enough data, especially, but in general, even in some situations, even with enough data, we may just be giving so much flexibility to the model that it can fit something that is not true. This is overfitting, is always a possibility with highly flexible models, right? So if you know something about the structure of the problem, if the nature of the problem is spherical, then you should definitely set that. Okay, I just realized I am definitely past time. So thank you very much for sitting through with me. See y'all on Friday.